Did you know there's a type of computer in development that could potentially solve problems in seconds that our current best supercomputers would take thousands of years to tackle? This is the world of quantum computing, a revolutionary field that many believe could redefine technology and transform our lives. But what exactly is quantum computing, and how does it work? Today we're diving deep to explore how this next-generation tech functions, why it matters, and where it's headed. First, let's take a quick look at classical computers, the kind most of us are familiar with. In a classical computer, everything boils down to bits, which represent either a 0 or a 1, a sort of digital on or off switch. These bits combine to create complex data structures and enable calculations. But ultimately, they follow a strict, linear path of processing, which means even the most advanced classical computers can struggle with highly complex problems. Quantum computers, however, turn this concept on its head. Rather than bits, they use something called qubits. Unlike a traditional bit, a qubit can exist in multiple states at once. This capability is due to a concept in quantum mechanics known as superposition. Imagine flipping a coin. In a classical computer, you would either have heads or tails, one fixed outcome. But in a quantum computer, thanks to superposition, it's as if that coin is in a constant state of both heads and tails until we observe it. This ability to hold multiple states at once allows quantum computers to process a vast number of possibilities simultaneously, making them incredibly powerful for certain types of calculations. But that's only part of what makes quantum computing special. Another quantum principle called entanglement plays a big role. When two qubits become entangled, their states become linked, so that a change in one qubit will instantly affect the other, regardless of the distance between them. This means quantum computers can coordinate information across their qubits in a way that classical computers simply can't, leading to unprecedented speed and efficiency in certain computations. So, why is this so important? And what could it mean for the future? Quantum computing has the potential to revolutionize many fields. For example, in drug discovery, scientists often face mind-bogglingly complex molecular interactions that are almost impossible to simulate accurately on classical computers. With quantum computers, however, they could simulate these interactions precisely, opening doors to new medicines and treatments faster than ever. In finance, quantum algorithms could optimize trading strategies and analyze financial data on a scale previously unthinkable, offering new ways to manage risk and predict market shifts. And in artificial intelligence, quantum computing could supercharge machine learning algorithms, leading to more powerful AI capable of complex problem solving. Even climate modeling, logistics, and cryptography could see massive advancements with quantum tech, handling calculations that are currently beyond our reach. However, as exciting as this all sounds, quantum computing is not without its challenges. One of the biggest issues is that qubits are incredibly sensitive to their environment. Any small disturbance, even a minor temperature fluctuation, can cause them to lose their quantum state, a phenomenon known as decoherence. Because of this, most quantum computers need to operate at extremely low temperatures, close to absolute zero, which requires specialized cooling systems that are costly and complex. Additionally, because the field of quantum computing is still emerging, we haven't yet fully developed the software and error correction methods that would allow quantum computers to perform reliably on a large scale. Despite these hurdles, governments, tech giants like Google, IBM, and Microsoft, as well as startups, are pouring resources into overcoming these challenges, racing to achieve what's known as quantum supremacy, the point at which a quantum computer can solve a problem faster than a classical supercomputer. In fact, we're already starting to see early signs of this. In 2019, Google claimed to have achieved quantum supremacy when their quantum processor, Sycamore, solved a complex mathematical problem in just 200 seconds. A problem that they estimated would have taken the world's most advanced classical computer around 10,000 years to solve. While some experts debated Google's claim, it marked a significant milestone in quantum research and hinted at what's possible. So, what's next for quantum computing? Many experts believe that while we're still years, perhaps even decades, away from fully scalable, error-corrected quantum computers that can tackle real-world problems with consistency, the breakthroughs we're seeing today are setting the foundation. As quantum computing evolves, we could see a future where industries like healthcare, finance, and technology itself are transformed. Imagine finding cures for diseases in days rather than years, optimizing global logistics networks in real time, or creating ultra-secure communication systems using quantum encryption that's virtually unbreakable. Quantum computing could unlock solutions we haven't even imagined yet, addressing some of humanity's biggest challenges. But, as with any technology, it's crucial to remember that it also brings ethical and societal questions. With great computational power comes the potential for misuse, particularly in fields like cybersecurity and AI. As quantum technology becomes more widespread, it will be up to us, policymakers, technologists, and society at large, to navigate its development responsibly. So, as we stand on the brink of a new computing era, one thing is clear. Quantum computing is poised to be a game changer. The road ahead may be complex, but the potential is almost limitless. If you're as fascinated by this as we are, make sure to subscribe because we'll be covering more revolutionary tech topics in upcoming videos. Until then, thank you for joining us, and stay tuned for the next episode.